a Hamilton path is different than an Euler path. For the Euler path, you wanted to traverse every edge of the graph. And that would be something important to, say, a newspaper or mail carrier, because a newspaper deliverer or a mail deliverer, they have to visit every street because they deliver mail everywhere. Well, for newspapers, they don't deliver everywhere, but they have enough customers that they have to traverse every street. And so for Euler graphs, what you're interested in graph theory is to traverse every edge. Now, when we move to section 14.3 and talk about these Hamilton paths and circuits, it's a different question. And the question is, think about the FedEx person or the UPS person. They're making deliveries, but they don't have to go down every street. In fact, when they load up at the warehouse, they have probably in their GPS that tells them all the customers in, say, you know, in the county, not really the county, but if it's a rural county, I guess it would be the whole county, but they have to deliver to individual houses. And the houses themselves are the vertices, where the deliveries go. And a UPS guy doesn't have to travel down every street because usually there's just, you know, one delivery on this street and 2 deliveries on this street and no deliveries on the next 3 streets and so on. So you don't have to go down every street. You just have to go to all the houses that have deliveries. So in a Hamiltonian path and circuit, you want to visit all the vertices, but you don't have to visit all the edges. So that's what we're talking about. Okay, so let's take a look. Hopefully that intuitive definition. Just remember that you do not have to traverse every edge for a Hamiltonian path, Hamiltonian edge. You just have to hit every vertex. All right, so let me draw one here. And it says, you know, find A. So there's many of them that you could draw here. So it says begin at A. Generally, you don't have to begin with A, but that's the part of this problem. And you want to end at G. And you have to visit every vertex. So we'll start here and we'll go there because now we have A and B. And then we'll go to here as our second edge. And then here, keeping in mind that we want to end down here at G. And then we're going to go up to D, make that delivery, and down to F, make that delivery. And then finally, come down here and end at G. So there is a path that would visit every vertex. We start at A, then go to B, and then C, and then E, and then D, and then F, and then G. We visited all of the vertices, but we didn't have to traverse all of the edges. There were several edges that we did not traverse. So when it says find a Hamiltonian path, just follow my arrows there. We start at A, and then we go to B, and then to C, and then down to E, and then to D, and then to F, and we end at G. Start at A, end at G. Find a circuit that begins at F. So now we're going to begin down here and ends with the pair of vertices D, then F. This one is a circuit. So if it starts at F and it's a circuit, it has to end at F. So F, and then how many? 1, 2, 3, 4, 5, 6, 7. We have 7 vertices, and we want to end at D, F. So we're going to have 8 letters here because we return to F. So we need 5 more spots. Okay, so find a Hamilton circuit. That means you begin at F and you end at F. And not only do you end at F, right before ending at F, you want to visit D. All right, so A, B, C, E, and G all have to be inserted in here once. And you want a circuit. All right. So I don't want to go to D from here. I want to do that I want to come back and do DF last. So maybe I'll do this. We'll see what happens. All right, so maybe I'll go down to G. And then sometimes a little trial and error. 1, 2. I'm going to try to avoid D. So I don't want to go to D because I want to do that right before. I just want to make sure I chart out a path so that I can hit DF at the end. So then we'll go to C, and then we'll go to B. I don't want to go D, so I want to go here. Now, the other thing about a Hamiltonian path is that you do not want to visit the same vertex twice. That was permitted in Eulerian graphs, Euler graphs. It was permitted to visit the same vertex twice, but in Hamilton paths, that doesn't happen. And then once we're here, then we can kind of come down here and we hit D and then F, 6 and then 7. So my path, it says find A, so that means that there's many. And my path was G and then E and then C and then B and then A and then the DF. And a complete graph is a graph that has an edge between every pair of vertices. And so let me just show this one up here. We would say that this one here is not a complete graph because while C goes to B and E, there's no direct edge from C to G. There's no direct edge from C to A or C to D or C to F. In a complete graph, there would be edges from every vertex to every other vertex. So this one here is not complete because, for example, to be complete, we would need an edge down to D. And we would need an edge to C. And we would need an edge from B to C and from B to D. And we would have to add a bunch more. But this one is not a complete graph because we don't have an edge from every vertex to every other vertex. However, this one is a complete graph because we have 4 vertices. A goes to B, A goes to C, and A goes to D. B goes to A, B goes to D, and B goes to C. And C goes to B, A, and D goes to A, B, and C. From every vertex, there is a direct edge to every other vertex. If that happens, complete graph. Okay, now if we know we have a complete graph, then there's this theorem in there. Every complete graph with 3 or more vertices has a Hamiltonian circuit. So up here, they were just asking you to find one. And then what they're saying down here is that since there is an edge from every vertex to every other vertex, you can start anywhere and you can go to any vertex and there'd always be a path to every other vertex. And you can create a circuit pretty easily. Now, know what this is saying here. It says, this graph right here is not complete and it has no Hamilton circuits. But here was a graph that was not complete that did have a Hamilton circuit. So it doesn't mean that incomplete graphs do not have Hamilton circuits. What this theorem guarantees is that if you do have a complete graph, you will be able to have or sketch a Hamilton. All right, and they tell you the number of Hamilton circuits in a complete graph with n vertices. 1, 2, 3, 4. So n is equal to 4. N is equal to the number of vertices. What this theorem down here says is that if n is 4 in a graph like this, not only can you find a Hamilton circuit, but there's this many of them. So if n is equal to 4, and we put 4 in there, this is n minus 1 factorial. And this is a math function. And if we put 4 in there, we get 3 factorial. Now, a factorial is on your calculator. And the way factorial works is that whatever the number factorial you're taking here, what you're going to do is you're going to start with that number and multiply it by all the other whole numbers less than it, all the way down to 1. So 3 factorial is 3 times 2 times 1. We recognize that to be 6. On your calculator, there's a function. It's in the math menu. So if I wanted to take, say, 5 and then factorial, that would be 5 times 4 times 3 times 2, and you stop at 1. So if you multiply all those numbers together, well, you get 5 factorial. Well, what's that? 5 times 4 times 3 times 2 times 1. That number. Now, if you just want to go right to factorial, it's in the math menu. And if you go over to the far right menu over there in the probability menu, see that exclamation point right there? I don't know, it might be on your calculator somewhere, but I know it's in this menu. So we'll do number 4 and see how it puts an exclamation point. That's our math function factorial. And this is how we define it. So when you evaluate it, you should get the same thing. All right, so determine if the graph must have Hamilton circuits. Explain your answer. All right, so what they want you to do here is to use this idea up here that this is not a complete graph. So there's no guarantee that you'll have a Hamiltonian or a Hamilton circuit. Whereas this one, 1, 2, 3, 4, 5, 6, 7, there are 7 different vertices. And there are no loops, so D doesn't come back to D, but D goes to all other vertices. So if you just do the degree, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, you'll find that the degree of every vertex is 6. And there's not multiple edges going to the same edge. I mean, for example, there is no 2 edges that go from E to D. There's just 1. And so because this is a complete graph, we know that this graph has Hamiltonian circuits. In fact, we know that there are 7 minus 1 factorial, 6 factorial Hamiltonian circuits. That's a lot of Hamiltonian circuits. 6 factorial is 720. So what that means is that if you wanted to list all of the Hamilton circuits, up here we found just one. Here. If you wanted to find all of them, there would be 720 different Hamiltonian circuits in this graph. And I think this one, there turns out to be none. But the theorem only guarantees that, I mean, we're not guaranteed one because it's not a complete graph. Okay, so this one's not too interesting. Determine the number of Hamiltonian circuits in a complete graph with the given number of vertices. Yeah, so you just take 1 less than that factorial. And then 13 minus 1, 13 minus 1 is 12, 12 factorial. We've already done this one as 6. I mean, these factorials get very large very quickly. $12 factorial. Yeah, you can see quite a few. 479 million. Hamiltonian graphs. All right, now to actually solve some problems related to Hamiltonian graphs, complete graphs, we're going to look at weighted graphs. In weighted graphs, what they're going to do is they're going to put a number on each one of the edges. And so now each edge has a weight. If you want to translate this to the UPS delivery person, then you could say, well, there's like 179 miles to get from D to C, or yards, or whatever unit of measurement, kilometers or whatever, hectometers. So 179 from D to C, 126 miles from C to B, from B down to D, it's 155, and so on. So you've got these units attached. What they're doing here is they're saying those numbers represent airfares. So let's say that you had this business person who had to travel to all of these cities in this area, and they only want to know how many frequent flyer miles they would have. Then each one of these numbers represents a dollar amount. It costs $190 to fly from A to B. It costs $179 to fly from either C to D or D to C, and so on. So there's a weight attached to each of them. Now, you're not going to make all these flights if you want to visit A, B, C, and D. You know, you're going to start somewhere, maybe here, if this is your home airport at A, at Atlanta, and you know, you want to fly to B, visit B, and then you want to fly to D or C. So you're either going to fly here first, then here, or you're going to fly here or and then here. So you want to visit the sites and then maybe come back to the starting flight because you've got to return home. What's the shortest amount or the least amount of money that you would have to spend to visit all 4 of those cities? Well, you'd actually visit 3 cities because you're leaving from home. So a circuit beginning at A. So this is a tough problem. This is a problem that we're working on here. And we'll have a couple of different ways to answer that. What is the minimum amount that we would spend to fly to those 3 cities? All right, so this first graph is a complete graph. You can see 1, 2, 3, 4, 5 vertices. Five vertices. And so that means you have 4 edges. The degree is 4 from every vertex or at every vertex. And the reason it's 4, it's 1 less the number of vertices because you're not going to go from D back to D in a complete graph. Okay, so find the weight of the edge BD. Here's B, here's D, there's the edge. And the only number sitting on that edge is 7. So the weight is 7. Now, if we're talking about a circuit, we have to start somewhere and end at that same somewhere. So here we're starting at A and we're ending at A. All right, so for this one, I'm going to draw the circuit on the graph. Remember, we don't have to pass through every edge. We have to pass through, but we do have to hit every single vertex. So we're going to start and end here to make up our circuit. And then we go to B. All right, so from A to B, B's over here. All right, so from A to B, the weight is 9. And then we go from B to D. All right, so here's B and D's down here, so we have to go this one here. That's number 2. And the weight of BD is 7. So from B to D is 7. And so now we're sitting here at D, and we're going to go next to C, and C is here. So then we go over here. It's our 3rd edge, and its weight is 4. And then from C to E, E is way over here. So that's the 4th edge of our path. And its weight is 11. And then finally, from E, we go back to A, and the weight is 10. So the total weight is just adding up all of those numbers there. 16, 20, 31, okay. Looks like 41. All right, why don't you try this one here. If you start at A and end at A again, is the total weight of the circuit going to be 41 again? I mean, after all, you're starting and ending at the same place. Why don't you figure out the total weight of this one? Okay, I agree. There were a couple answers of 31, and I'll agree. What I want to point out here is that you can have 2 different circuits in a Hamilton, two different Hamilton circuits here, but they have different weights. And if you did another one, and there are many, right? How many are there? 5 vertices, 4 factorial. We just have 2 of them. of the 24. I wonder if we did all 24, if we would find something smaller than 31. Let's say it cost you $10,000 for every mile driven. So if this was $8,000. If you had to pay that amount of money, then you'd be very interested in getting this number down as low as possible. And hence we have the traveling salesperson problems. It's basically this problem up here. If you do have a complete graph and you do want to find a Hamilton circuit, that is, you start and end at the same place, what is the minimum weight? Is it 31 or is there something smaller? So there's been lots of problems that there are lots of ways to find that over the years. And one of them is called the brute force method. That is, write down every possible circuit that you can write down. Now this one has 1, 2, 3, 4 vertices. And if you subtract 1 from that, 3, and take 3 factorial, you will get 6 different Hamiltonian circuits, or Hamilton circuits. And so what they want you to do here is to use this weighted graph and then determine what the sum of the weights are for each of the edges. Now we're going to jump from A to B, that's 1, from B to C, 2, from C to D, 3, from D to A, 4. So there's 4 numbers you're going to be adding up here. And then the total cost would be the sum of the weights. So these must be costs. But this is called the brute force method because, you know, you're just going to grind it out, you know, list all the possible circuits and then add them all up and see what happens. All right, so we go from A to B, that's 20, and then over to C, it's 15, then over to D, that's 50, and then back up to A, that's 30. For this one, we go from A to B, again, that's 20. And then once we're at B, we go to D, it's 10. And then once we're at D, we want to then go to C, which is down here. And then finally back up to A, which is 70. And on and on and on. And so you might find that some of these weights match. You might find that none of them match. Depends on the size of the graph. So I think this one is 115, 35, 65. This one is 30, 150. All right, so you can see there's a difference. All right, so from A to C, down here, that's 70. And then C to B, 15. And then from B to D, 10. And then finally from D to A, which is the 30. And that's 125. You would just continue with these, adding 4 numbers in each of these 3, and then you would inspect all of these total costs. And the total cost that's the smallest, that would be the solution to the traveling salesperson problem. They've done this for us really, but model the problem with a complete weighted graph. Okay, here's our complete weighted graph down here. Make a list of all possible Hamilton circuits. And it's sufficient to just choose one of the vertices to begin with. So if you began this first circuit up here at B, then you would go B to C to D to A, and then back to B. And that circuit would be the same as this one. So we don't replicate them. It is called the nearest neighbor. The problem is the nearest neighbor method doesn't always give you the best solution, but I want to go through it anyway. So here's an example of the nearest neighbor method, starting with vertex A. So usually in these problems, they'll give you a starting point, like A. So we're going to start here, and it's a circuit, so we want to visit E and B and D and C, but then we want to return to A to make up the circuit. So where do we go first? Our choices are down to B, that's 500, down to C, that's 200, down to D, that's 185, or down to E, which is 205. So we compare 205, 185, 200, and 500. And of course, these are not drawn to scale because 500 should be a lot bigger than, 185, but it just doesn't appear that. So these complete graphs are not drawn to scale. But for the nearest neighbor method, you choose, imagine that these are miles, and then what's the shortest distance from A to any one of these? And of those four numbers that we identified, the smallest one is 185. So we would say the nearest neighbor to A would be D, and that's where we're going next, or we're going first, I should say, 185. So now we're sitting here at D. Now we don't want to return to A until the end, so we're not going to just traverse back to A again, even though 185 may be the shortest. So, we're not going to traverse that one again. But what is the nearest neighbor to D other than A? Our choices. This is a complete graph, so D goes to all the other vertices. 302, 360, or 320. What's the nearest neighbor? That, and that. Well, 302 is the shortest number of miles, so it's the nearest neighbor. So if we go to the nearest neighbor, then from D, we're going to go to E, and that distance is 302. All right, so now we can't revisit D, we can't revisit E, and we want to wait to go back to A at the last thing. So our choices are either B or C. So from E, now we don't want to go back up to A because that would complete our circuit, and we want to complete the circuit as the last step. So we don't want to go there. So our choices are to go over to B or down to C. So between 340 and 165, what's the nearest neighbor? In other words, what's the lowest weight? And it's 165. So we're going to go down to C, 165. And at this point, there's no other place you can go because B has to be here because it's the only vertex that we have not yet visited. So from C, we have to go to B because we want to go to A at the end. We've already visited D, we've already visited E. So from C to B is 305. And then finally at B, to complete the circuit, to return home to our home or to our home city or our home airport or to the warehouse, whatever it is that we're returning to, we need to go back to A, and that's 500. And the total weight is 1457. All right. So these are not miles, but as you can see here, sales director needs to fly. Okay, so this is another flying from the cities B, C, D, and E. Starting at the home airport of D, these are the amount that the flights cost. And if you add up all these amounts to make the entire round trip, $1,457. And that would be the minimum cost using this method. But the thing is, this method doesn't always give you the minimum weight. So there may be a cheaper one. And if we wanted to find a cheaper one, the best thing we could do is the brute force method. But there are 5 vertices, so there's 24 different. And this describes the nearest neighbor method.